Drosophila melanogaster PMCA, PM, PJ, PS, and PS. All three isoforms have exact match, and also almost 90% match with these other isoforms as well.
Wait a minute, I got the wrong one.
Right? And if you look at the results,
So,
summary,
you didn't? No, that was already.
look at that.
You gotta
All
take this off.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All 11 isoforms has expected value 0, right? So whenever you do a blast search, always look for which one gives you a 0 expected value and maximum score, right? So it has a maximum score that it is 2,200 base. Score. And also expected value is 0. That means it is not by chance. It has an exact sequence match from the database, right? The protein sequence from our Contig 11.1.
Scroll
Now,
down.
and now this tells us, okay, apparently it shows that our Contig 11.1 is a PMCA gene, right? Right? It codes for PMCA protein, right? Now, still we don't know, because now all we have to look for that what is the location of this gene, because we took that Contig 11.1 from dot chromosome, like chromosome 4, right? Now, since it has a match with this PMCA gene, we want to see whether Drosophila melanogaster has the same location in dot chromosomes as well or not. Can you guys follow me in that? Right? Did you get me? Right? So we took the predicted protein sequence and we are doing the BLAST-P search with this fly-based database, right? From Drosophila melanogaster. So apparently it shows that our gene of interest, our protein of interest, has the exact same matching with this PMCA gene, right? Now, we want to see whether they both located at the same location, because our Contig 11.1, we have taken this sequence from dot chromosomes, right? Chromosome number 4. Now, if you click on PMCA from Drosophila melanogaster and click on this sequence and look at their location, look at that. It has the type protein location 4. Location 4 means it's on the chromosome 4. That tells us that also this gene from Drosophila melanogaster is located on chromosome 4 as well.
What do you see location?
Wait, what did you?
Where's the location?
No, yeah, or you can scroll down, or you can click on this sequence score. It will show you the location of this. So remember that.
Mr. Umar,
Yes.
could you assist me? Something's going wrong.
Oh, it's not showing
Yeah, it's,
gene ID,
but it's not.
gene scan ID.
This is different now from what I originally had.
No, you see that predicted protein.
Because it's coming out with.
Yeah, Contig 11.1.
But you see them on a base pair, is that what?
Yeah, this is the predicted protein sequence.
Yeah, but it was just previously 7.
Okay, copy that and go to flybase. Yeah,
Yeah, but this
yeah,
was
that's
different.
oh,
Yeah, it was different.
It's
That's what I'm trying to say.
okay.
Your base pair look was different from mine.
What is did they put Contig 11 in there?
Yeah.
Okay. Oh, it probably didn't change the Drosophila grimsoid. Did you? Like you have to change it from here. We are going to see the sequence from Drosophila grimsoid. That is where is from Drosophila grimsoid. Okay, and then from 2009, and then Contig 11.
I forgot to change it back.
And then you click on the now predicted protein and copy that and do the flybase. So do you guys follow me now? So now this tells us that our Contig 11 codes for a protein that has exact similarity with the PMCA genes from Drosophila melanogaster, right? And they're both located on the same, on chromosome 4, right? So now we have two parameters. consider. One is it has the ortholog of, we can predict that it may be the ortholog of PMCA gene, and they both located at the same location, right? Right, on chromosome 4.
Yeah.
Now, the second thing we're gonna look is what it says. Now, use your protein sequence GeneScan to search a database of all Drosophila melanogaster. Provide a copy of the top 20 hits and briefly describe the results. So results means you can just explain it like, okay, first 11 gene has expected value 0. Yes.
What does the score mean?
The score. So the score basically tells you how many base pair matches with that, right? So if you look at this score in BLAST, and just double check BLAST search.
So what were you saying when you were talking about
The quality, higher numbers corresponding to higher similarity. That's it. The quality, yes.
How do I open it?
And it apparently is on the like if you have a base to base match, it is considered probably 1 point, I guess. The algorithm. Okay. Now as you can see here, the higher quality matches with that an expected value 0, 0, 0, and then the bottom one has less. And obviously, look at that. Even it has E, but it still is bigger than 0. Whatever you have E negative 76 or whatever, that means 0.0000 up to 76 and then 1. So 0 is absolutely 0, and then these are not absolute values, so these are less than or greater than 0 in fact. Okay. Now the third question is asking about, let's go to now this, that the assumption we are assuming that it has a P is basically the contig we are analyzing is a PMCA gene, right? Now we have two evidence. That one is it has exact match with the protein sequence from Drosophila melanogaster, and the other end they both located on the same location.
So,
right?
real quick, with the screenshots, do you want us to get the top 20 and the color diagram?
Yeah.
Okay.
Take a color diagram and then take this tables picture, screenshot.
Just a quick question.
Yeah. Yeah, it's fine. Just take first, because we're not going to consider this.
Okay, so just.
It's fine. Okay, but you have to take this table and you have to
Done.
analyze what you mean from this table.
Yeah, I got the table.
Now, what is the third question is asking you? Now, as you can go through, while the GeneScan prediction shows significant matches to this, it doesn't necessarily mean that predicted gene model is correct. As I said earlier, like only 23-30%, even though the computer predicts that it is the PMCA gene, comparing with the Drosophila melanogaster database, but we are not yet sure, right? It's like it can be wrong. Like most likely it can be wrong. Only majority of them are wrong, even though it predicts the same similarity type. Okay, now all we know that BLAST has aligned at least some contig with some PMCA in Drosophila, and the total sum of alignment gives us a good E value. Therefore, the similarity search have convinced us that PMCA is probably in here somewhere, and it overlaps with the GeneScan prediction to a large enough extent to give a very good BLAST result. Okay, now all the isoforms. In order to do an exon, now we want to see exon by exon, like part by part. So this is like a gross idea we are getting to assume that it might be PMCA gene. Now we have to look deep into that process, like by analyzing each of the exons that has the similarity, whether they have the same exon size or no, whether they have the exact position of the splice acceptor and donor sites. Now, put a copy of this series. Now go to this again, annotation PMCA, and then now you have to go to this side again, the GEPWS site. So I'm going to go there, and then you go to Gene Record Finder this time. Gene Record Finder and write PMCA. We want to see how many exons in PMCA gene in there, right?
Said gene.
Record Finder. In the project section,
Yes.
you will see Gene Record Finder, right? You can follow me. So this is case sensitive, so I'm writing PMCA here. As you can start writing in there, you can see,
Yeah, it comes up.
yeah, and it's the mRNA, 11 mRNA, number of exons 26, 20 databases. They found this kind of thing. So I'm clicking on the record finder. So first we have to look into the PMCA gene to analyze our gene of interest. Right? As you can see, it shows how many exons are there. So these are the isoforms, these are the number of exons in there. Can somebody tell me how many exons are there?
Wait, where's it?
Is it 10?
17.
For which one? No, it's well, it depends on which one.
Now look at the isoform PO.
Oh, PO,
Oh, PO.
How many exons?
17.
8.
Oh no,
The middle tree is missing, so it's
Sorry,
basically
14.
14 isoforms, right? And like 14 exons,
14
right?
exons.
And then these are the isoforms. So how many isoforms of this PMCA gene? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right?
So the isoforms.
Now look at that. The isoforms are basically the same gene, but due to splicing or over the time of evolution, it makes it becomes a variable. I mean, it varies.
So it's
Variance.
11
A
isoforms.
variation. It's basically the same gene.
Okay.
So
And
it's not
so
like
we'll-
recombination. Recombination.
It can happen recombination or splicing. What is that called? There's this term that says like if splicing
Not
variation
alternative.
due to alternative splicing.
Alternative splicing.
Due to alternative splicing.
So we still need to take a picture of this.
Yeah, you can take a picture of this. Now, as you can see, the interesting thing is like protein isoform PP. Look at that PP. It has missing the number 5 exon, right?
Correct.
And then, so also the other isoforms are missing. Some of them have common, like, so you have to analyze this whole table, like what do you see from there? So for example, you can say, okay, PP has missing 5 exon, like 5 number, you can
GEP.
look at that number 5 isoform PP may have
Go to the
missed
record
this number,
finder.
exon number 5.
Oh, these are they different?
Yeah, like the differences and
And
similarities. So
PMC.
majority,
PMC.
I mean, all of them has like
PMCA.
first 4 common, right?
PMCA.
And also 6,
PMC.
7, 8, 9 are common. That means they are conserved in all isoforms, right? And also I would say from 6 to 12 or 13, I guess 14,
You gotta go back to all
15, up to 15.
to whatever it was you were
So you can just summarize it that
main
The,
blast.
so we
All
can talk about isoforms. we can talk
isoforms,
about
what
the
do you
exons.
see from this? What can you infer from this table?
So with this table, what does that red mean?
The red?
Because I noticed between 15 and between 15 and exon 16.
Oh,
on
the color
PMC.
diagram, right?
Yeah, what does that mean?
The color means,
At the top where it's red.
I think, yeah, because some of them are white, some of them are red,
Yeah.
right? No, basically if you click on
Oh,
that,
if you
then
click
it
on
becomes red.
Oh, okay.
It's
Sorry.
basically white.
So that's pretty much. So,
Uh-huh.
are those?
They are missing.
Oh.
They are not in there. They are not present in that isoform. For example, isoform PO don't have 16, 17, and 18 exon,
Gotcha.
right? So you can find the similarities that most of them has common until 15 isoform, but except PP, it has missing chromosome number. I mean exon number 5, right? Do you see that from there? You didn't get it? Go to Gene Record Finder and write PMCA.
Where? PP?
Gene Record Finder.
I'm on the
Or if you go to this side, the project, and then if you click on that under the annotation resource tab, there is a Gene Record Finder.
So you said PP has missing.
Exon 5. Do you see that
Exon
blank
5.
space in there? Oh, Gene Record Finder. Right? Click on that. Or you can go this way. Now click on that. Oh no, not the go to projects. Gene Record Finder. Yeah, now you got it. Now write PMCA, all caps. This is case sensitive. Yeah. Now enter. Scroll down. You look at that. The same table you have. So you have to write down what you see from there.
Like, how do you describe it?
Oh, so these are basically number of isoforms on the left, the column, and on this side, on this row, you see there, these are the number of exons. So if you scroll through that, you can see that number this isoform PP has missing exon number 5, and also some of them like isoform PO don't have the 16, 17, and 18 exon.
So we will talk about that. how
Yes,
that's-
talk about that. What do you see from that? Just analyze this table, right? Which one has similarity? So most of the majority of them have, I mean almost all, except PP, has common from 1 to 15 exon, right? Now, if you click on that isoform, any of the exons, it will show up the protein sequence from there. For example, I want to see chromosome 1, I mean exon 1. So if you click on that, exon 1 on the column, you see the amino acid it codes for, right? So the
Oh,
next
you
part,
click on which one? Exon 1?
exon 1. So exon 1, exon 2, exon 3, exon 4, 5. So if you click on the column, the top, then it will show up your exons. I mean the amino acid that exon codes for. So exons are like coding sequences, right? Exon 1 that will code for a specific part of a protein, portion of a protein. Now, all you have to do, the second part is asking you, so you have to analyze it, how many isoform exist for this, how do these isoform differ with respect to the coding exons, right? So you know how to do that, right? Question number 3 is done then. Now, to map each putative exon position, we will use the align 2 or more sequence functionally in NCBI BLAST to compare 2 sequences. Now we have to go to the BLASTX again. So go to BLASTX now this time. Okay, now for the BLASTX,
I have
all
a question
yeah.
about the protein. So you said that PC and PP5, exon 5 is missing,
Mhm.
but it just says 5 right here. It just think it's shifted.
Oh, because it's missing means like they counted 1, 2, 3, 4, 5. So this region is missing. So the next one will be 5 definitely.
Oh, okay. Thank you.
Which question are we on for?
We are on 4 now. Now all you want to do, so we are now analyzing our PMCA gene from Drosophila melanogaster, right? So we figured out that PMCA gene has that many isoforms, and they're, because it has been done by some other people and it's very well defined. Now we want to use this isoform, each of the exon sequence, to compare with our unknown sequence, right? From contig 11 to 1, 11.1. Do you get my point?
Are you talking about the unknown from what we had last week?
No, the contig
Oh.
11.1,
Oh, okay.
the one we are analyzing.
Right.
So this time, so here is the chronology. They will give you a sum up, like what we are doing today.
Oh, you said we need to
So we are analyzing contig 11.1 from Drosophila gramsci.